Welcome to Almost Here, Round the Corner Future Technology podcasts with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with the Future Tech Podcast. My guest is Mr. Jussi Luntama. He's ESA's head of space weather, and ESA is the European Space Agency. We'll be talking about the new mission, the Lagrange mission, that's going to monitor solar activity, because as I'm sure a lot of people know, solar activity can dramatically affect what goes on Earth, with satellites and communication equipment and everything. So, Jussi, how are you doing today?
I'm good. Thank you very much, Richard.
Yeah. So tell me about this mission. What does it entail? And we're monitoring the sun, but from where? What's the mission going to look like?
Yeah. Well, Lagrange mission it's a mission very much encouraged by the success of the NASA stereo missions, actually, because stereo mission contained two spacecraft which were flying around the sun from the Earth perspective. And they were looking at the solar activity from different angles and different locations. And that encouraged us to actually look at the possibility to establish something which we could consider as a permanent operational stereo mission, that we would have one spacecraft in a specific location, which we call the fifth Lagrange point, where we can actually see the solar activity from a different perspective than what it looks like when we look towards the sun from the Earth.
Well, so what is the Lagrange point, and what perspective is it that we're not seeing right now?
Well, the Lagrange points in general are the points where the gravitational pull of the sun and the Earth, also considering the orbital mechanics, they balance each other out. So basically the Lagrange points are the points where the spacecraft is in a stable position, not pulled towards the sun or not pulled away from the sun. And the fifth Lagrange point is actually, it's not exactly a point, it's kind of a plateau. It's an area which is on Earth orbit, 150 million kilometers behind the Earth. And if we park a spacecraft there, it will stay there essentially forever. And we don't have to keep its position there. It will be trailing the Earth from this 150 million kilometer distance until eternity, unless we move it away from there at the end of the mission. And the idea of this point is that we are then looking the space between the sun and the Earth from the side. And that means that when something nasty happens in the sun, which is potentially a risk to the infrastructure on the Earth, particularly when there are events called coronal mass ejections. Basically, they are kind of explosions in the magnetic field within the atmosphere of the sun. And then as a result of these explosions or eruptions, billions of tons of the plasma from the sun itself, so the solar matter, is ejected into space at speeds reaching up to 3,000 kilometers per second. And when these plasma clouds hit the Earth, they will not threaten the life on Earth. On Earth, we are perfectly safe, but our infrastructure does not like these impacts. So our satellite systems are at risk, or even the infrastructure on the Earth, particularly the power grids, are at risk. And if we can see these plasma clouds from the side when they are propagating towards the Earth, we can estimate their speed and the potential hazard from these clouds more precisely. And we can also see the direction, because these clouds, if they go a little bit too high, a little bit too low, so that they don't impact the Earth directly, then the risk on the infrastructure is much smaller. And we want to inform the people who are operating the infrastructure about the risk before the impact.
Well, there are two questions. One, how do you avoid the satellite not getting fried by the incoming, coronal mass ejections? And is there anything you can do if a big one is coming, can we, I don't know, shield the equipment somehow or turn it off or have it run in a band of frequency that will be less affected by the plasma that's coming?
Yeah, I mean, that's a good question. Actually, for the satellites, the safest way to handle these situations is or would be actually to turn the satellites off, because the electronics on board the satellites are much less sensitive to these impacts when they are not operating. So that would be one way to handle the situation. And if really a big one is coming, then a potential measure that some of the satellite operators would take would probably be to turn at least some of the satellites off, so that if the worst happens and we lose some satellites as a result of this impact, then we would have spare satellites in the orbit that would then allow us to resume nominal operations as quickly as possible. On the Earth, with the power grids, the situation is slightly different, because the option to turn the power off, even though that might help to protect the power grids, and particularly the transformers in the power grids that might be impacted, that would create a huge risk by itself, because a lot of systems would, of course, fail in that situation. So the best thing that the power grid operators can do is what they call balancing the grid. So basically, they would like to reduce the load on the power grid. They would like to make sure that all parts of the grid are in operation. There are no parts which are under maintenance. They would maybe even ask some big power consumers to reduce the consumption for a while, so that we can handle this geomagnetic storm that would start as a result of the impact of the plasma clouds. But in order to do or to take all these measures, people need time. And this is what we try to achieve with this Lagrange mission, that we would actually have more lead time when we give our warnings about what is about to happen.
Well, how long does it take for a CME to travel from the sun to Earth?
Well, that's a very simple calculation. The distance is 150 million kilometers, and if the CME is traveling at 3,000 kilometers per second, it takes about 15 to 17 hours to reach the Earth from the sun.
And if we have a satellite at the Lagrange point, how far out will it see? Will it see the CMEs as they're occurring right on the surface of the sun, and will we have the full 15 to 17 hours, or will it see stuff only when it's close and it's on its way?
Well, the situation is that actually we can see the CMEs even from the Earth. So that will not change. So we can see this onset, this ejection or the eruption in the sun that is creating the CME in both cases. But if we have both observations of the CME from the Earth, and then we have them also from the L5 point, so we have kind of a stereoscopic view on the CME, we can estimate much more precisely how quickly it's coming, so we can assess the potential danger of this CME. And then we hope that with the L5 mission, we will actually also be able to predict better when a potential CME eruption would actually happen. Or if we cannot tell the exact time when it will happen, at least we can give an early warning that people can start to make preparations even before the CME starts.
So what happens when a CME hits the outer atmosphere and the inner atmosphere, and does it actually touch the Earth's surface? What happens to the plasma as it interacts with the atmosphere and the Earth?
It does not really touch the Earth. I mean, Earth is really well protected against solar activity. So we have, first of all, we have the magnetic field, the magnetosphere of the Earth, which is deflecting a large part of the plasma which is coming from the sun. And then whatever gets through is basically absorbed by the atmosphere, at least to large extent. So at the Earth's surface, it's very rare that we actually see any particles coming from the sun. But what will happen is that depending on many things in the physics and in the orientation of the magnetic field outside the Earth's magnetosphere and the Earth's magnetic field and so on, some of this plasma can actually enter into the magnetic into the magnetosphere of the Earth, so it can basically get inside the magnetic field of the Earth, and then it disturbs our magnetosphere. So basically, the whole magnetic field of the Earth is disturbed. This is what we call a geomagnetic storm, and that creates a kind of a transformer type of situation where there is one part of the transformer in space within the magnetosphere. Another part is, for example, the power grids and the soil under the power grid. So we have two coils of the transformer, one in space, one on Earth, and that creates DC currents in the power grid, which is something that the power grids are not really designed for. And that actually can cause the damage in the transformers in the power grid. The satellites in space, what they don't like is actually these charged particles, the protons and electrons, that are triggered by the arrival of the CME, and then the electronics on board the satellites can be disturbed or even permanently damaged by these events. And then finally, of course, when we have also astronauts in space, these same particles that are disturbing the satellites, they are also creating a radiation hazard for the astronauts. So astronauts also, they would like to know in advance when these events are taking place, and then they will seek shelter in the better protected parts of the space station, for example.
That's okay. Yeah. How often do they happen? Like every few years, or monthly, or constantly, or how long?
The CMEs, I mean, normal sort of, let's say, small and medium-sized CMEs, they happen often during a active solar period. So when we have high solar activity, we have CMEs weekly. In some cases, we have them daily. But these really big ones, the ones that can really disturb and destroy parts of the infrastructure, they fortunately don't happen too often. The really big one, the biggest one that we know of up to today, happened actually more than 150 years ago in 1859. That was called the Carrington event, based on by the name of the guy who actually detected this event. And if that would happen today, we would definitely have a big problem with our infrastructure. Smaller events, but still big ones, have happened sort of once every decade. And now at the moment, we estimate that these really big ones, they might happen once every 100 to 200 years. And now the previous big one was 150 years ago. So does it mean that the next one is inevitable? That I don't know, but it will happen eventually.
What does it mean? I've read that, we're in a period of low solar activity, or we're in a period of high solar activity. I mean, besides the obvious, high solar activity, more CMEs, what's the consequence for Earth if we're in a period of low or high solar activity? Is there anything else that is important to know about it? Well,
what it really means is that when we have high solar activity, we have more these small and medium-size CMEs. For example, we have more often these eruptions in the sun that can also produce other things like solar particle events. So basically, we can have very energetic particles accelerated by the processes in the sun. And again, these are events that our satellites don't like at all, and also they would be dangerous for manned spaceflight. But these really big events, these devastating events, they don't actually really care about the solar cycle. So we have historical evidence that the big events have happened at the solar maximum. They have happened close to solar minimum. They can happen actually at any time during the solar cycle. So in that sense, if we really worry about the biggest events, the solar cycle is not that significant. We have to be always aware, and we have to be monitoring what's happening in the sun.
I don't know if this is a silly idea, but is there any way we could harness the material that gets ejected from the sun, at least a little bit of it? Build a device with tremendous capacitance, so when these charged particles come in, we somehow harness some of the energy, or is that just silly?
Yeah, that's an interesting thought. I mean, I think some brainstorming occasionally takes place about what we could do with this all this energy that is released by the sun. I have never heard of anything which would be really practical, something that we could really build. I think the best way to use the energy from the sun still today are the solar panels. These plasma clouds, they are fast, they contain a lot of energy. At the same time, we have to keep in mind that actually the plasma in space is extremely sparse. So still building some kind of a huge windmill or something that would utilize this plasma, the scales would be enormous. So it would be really difficult, technical challenge to build anything useful.
Okay. Yeah. What do we think is happening inside the sun to cause a CME? What's the mechanisms of what makes it?
Reasonably well, what happens, or at least we have a good theory about what happens. What actually happens in the sun is that the sun is just like the Earth. Sun has a magnetic field around it. Sun is essentially it's kind of a liquid. It's a ball, it's a huge ball of plasma with a nuclear reactor in the center. This flow of plasma from the really hot core of the sun towards the surface, it creates motion, convection of the matter. It's charged matter. It's moving. It creates a magnetic field, but the magnetic field of the sun is much more complex than the magnetic field of the Earth. So instead of just one north pole and one south pole, the solar magnetic field has multiple poles. And then it has small local anomalies where actually there can be a small region on the surface of the sun where there are a lot of north poles and south poles kind of mingled against or between each other. And then there are a lot of magnetic field lines between these poles. And then what people tend to say is that what happens is that when this mix of north poles and south poles and the magnetic field lines, it keeps changing and these fields get entangled more and more. It's like you take a rubber band and you twist it between your fingers and it gets more and more entangled. Eventually, the rubber band will break and it will hurt your fingers when it does that. When the magnetic field of the sun locally gets too entangled, it will also break. And then it will release the energy that was stored in the magnetic field. And that creates these eruptions that actually have so much energy that the plasma from the sun itself can actually be ejected into space in such a speed that it escapes the gravitational pull of the sun itself.
Has anyone thought to try to do something on a very small scale here on Earth? Create a bunch of magnetic fields and then twist them and, tie them up and then release them to create energy or release energy?
Yeah, I think actually this process, it's not a very good process of producing energy because you have to have first a lot of energy and then you can release some of that by this entanglement and the breaking of the magnetic field lines. So it's not a good way to produce energy, but it would be an interesting way to actually simulate and try to understand better what happens in the sun. But it's very difficult to do. We are not very good at keeping stable, keeping hot plasma within a stable magnetic field on Earth. I mean, as we know from the attempts to build fusion reactors. But what we are doing instead is actually we are sending satellites to study the sun and try to understand these processes more precisely. And the U.S. just recently launched the Parker Solar Probe, which will dive very close to the sun so that we can actually see these processes and understand them better. And ESA will actually launch in a couple of years the Solar Orbiter mission, which will complement the observations of the Parker Solar Probe. And actually then we hope that we can actually do scientific research that helps us to understand these processes better.
Yeah, I was going to ask you about the Parker Solar Probe. What can you say about it? When's it launching and when will it get close to the sun?
I mean, the Parker Solar Probe was actually launched. So it's on its way towards the sun right now. I don't know by heart when it will start to provide measurement data, but it takes a while to get into the right orbit because it needs a specific orbit where it's actually kind of diving towards the sun, making a very fast pass around the sun, and then it comes out again more or less to the distance of Venus from the sun, so that it can actually cool down a bit, transmit the data to the Earth, and then repeat this cycle several times. But it will get so close that it will get observations of these phenomena that are happening in the sun, and I hope that we will be lucky and we will actually see some of these eruptions in the sun while the Parker Solar Probe is working.
Is it going to be inside the corona of it, or what? How close will it get?
No, I mean, yeah, the corona is a bit hard. I mean, that's very hot. So actually, I don't think that you can get inside the corona, but you can get close to it, so that you have a better view, and also you can make some in situ measurements about the environment there.
Have we launched any, like kamikaze probes into the sun? Is that even possible?
It's a bit surprising to say this, but actually hitting the sun is not trivial. It takes a lot of fuel to actually break down from the speed of the Earth and then dive into the sun. So we have never done it, and I don't think that most people would consider that this would be very useful. Actually, this kind of a mission like the Parker Solar Probe that is orbiting around the sun but getting close to it, this is more useful because you have more time to make measurements, and you need to be a little bit lucky to get close enough to one of these events in the sun so that you get really the information about what's happening during these solar eruptions.
You said that we may be able to predict and model the CMEs. Can we do that at all now? And when we do predict it, how far in the future do you think we'll be able to predict, or is it like weather on Earth? You could probably do maybe a day, and that's about it.
Well, actually, to be honest, if we could do a reliable forecast of the solar activity for a day, we would be quite happy. At the moment, what we can really do well is to monitor what's happening and then follow what's happening when there is an eruption. Forecasting a solar eruption is, I tend to compare it to forecasting a tornado. We can tell when there are suitable conditions in the sun that there might be an eruption, but telling exactly when it's going to happen and how big it's going to be and where it's going to impact, this is very challenging. We really need these Parker Solar Probe and solar orbiter type missions to understand the sun and these processes better. But what we can do when we combine the measurements from the Sun-Earth line, which is what the U.S., particularly NOAA, is doing, and then the new observations from, for example, the Lagrange mission, we can give an early warning that now you should be aware that there is a potential for solar eruption. So take precautions and stay alert for further information, which we will provide as soon as we detect something.
So what's the roadmap for the Lagrange mission? When will it launch, and when will it be in position to start gathering data?
We are at the moment, we are still designing the mission. So we're designing the spacecraft, and we have prototyping activities for the instruments that we want to have on board. We hope that in 2020, we can start to actually build the spacecraft, and we can also start to build the instruments, the flight models of the instruments, which will be space qualified. That would take us to a launch some time around end of 2023 to early 2025, depending a little bit of the technical challenges in the final steps in the building the actual hardware and testing it and integrating everything together for the launch. Then flying to the L5 point. L5 point takes 14 months. So if we can launch, let's say, mid-2024, that means that we would be then in L5 in the second half of 2025, and then we would start to do the observations of the solar activity.
If you had a ruler, between the sun and the Earth, where would the L5 point sit? How close to the sun and how close to the Earth?
Well, it's the L5 point creates a perfect triangle. So if the distance from the Sun to the Earth is 150 million kilometers, then if you go backwards on the Earth orbit, so you basically go to the anti-flight direction of the Earth on the Earth orbit, 150 million kilometers, then that's where the L5 point is. And then it's on Earth orbit, so the distance from the L5 point to the Sun is again 150 million kilometers. So it's a perfect triangle with where each side is 150 million kilometers.
So does it literally orbit around the Sun, trailing the Earth, like a tin can trailing a car?
It's there. It's following the Earth perfectly. So it's always in the same spot in respect to the Earth, and this is really the advantage of this point. So when we park a spacecraft there and we point the instruments from the spacecraft towards the Sun and also towards this space between the Sun and the Earth, it will always remain in this position, so we can keep monitoring what's happening. The disadvantage of this point is that actually 150 million kilometers is quite far away. So it's a deep space mission. We want to download this data from this mission all the time. So this will be the very first operational deep space mission with continuous data download that mankind has ever built.
How long will it take data to come from the satellite to?
Yeah, that's another interesting point. I mean, it will take 8 minutes. So at the speed of light, the travel time from the L5 point to Earth is 8 minutes. So when something happens in the Sun, the photons from this event will take 8 minutes to reach the L5 point, and then the first bit of the image that we are taking from this event, it will take another 8 minutes to come to Earth. So 16 minutes is the total time from the something happening in the Sun before we have the first information of that on Earth.
Since the L5 point is a balancing point where an object, you said, will stay there forever, is there anything there right now? Do you think that just randomly asteroids or stuff that's gone through our solar system has gotten stuck there?
Well, that's another very interesting question. Actually, before the stereo mission, there was the thought that there would be so-called Trojan asteroids that would be there hanging around in the L5 point. But my understanding is that because it's not really, it's a plateau. It's basically if you have any speed and you do not have brakes, then you are basically drifting through it, and then you are slipping away from the other side. So basically, asteroids do not break. So there are no, as far as we know, and this is based on also what the stereo mission saw when it was passing by close to the L5 point, that there is no dust, there are no Trojan asteroids, there are no rocks there. So it's basically a clean, empty plateau where we can park our spacecraft.
Do you think Venus or Mercury have similar points that could be used, or other planets?
I mean, every single. I mean, this is the magic of the mathematics and the orbital mechanics. Every two-body system has Lagrange points. So basically, there are Lagrange points between the Earth and the Moon. There are Lagrange points between any planet moving around the Sun and the Sun itself. So these points do exist whenever there are two bodies with a gravitational pull, and you can calculate with relative ease where these points are.
Well, how could the other ones be useful? Like between the Earth and the Moon, is there anything? If we park a satellite there, would that be useful? Or maybe the Earth and Venus, or in tow behind Venus.
Proposals. Yeah, I mean, we haven't used those points yet, but there have been some proposals. So maybe we could park, maybe in the future someday, we could basically divert an asteroid to one of these points, maybe one of these Lagrange points between the Earth and the Moon or somewhere else where we can go and mine it. I mean, there are some ideas, but we have not utilized many of these points so much. The Earth-Sun Lagrange points, the L1 point, which is a point which is between the Earth and the Sun, relatively close to Earth, only 1.5 million kilometers away, we have several spacecraft there, most of which are actually for the monitoring of the solar activity and the environment in this L1 point. ESA also had recently a ESA Pathfinder mission there because this is a technology demonstration of technology to detect gravity waves in space. And then there is the second Lagrange point, the L2. It's a similar point behind the Earth on the Sun-Earth line. So there is also this stable point, which is 1.5 million kilometers behind the Earth from the Sun perspective. And for example, at the moment, ESA has there a mission called Gaia, which is mapping the stars in our Milky Way, because it's a nice point where you can build a spacecraft which is shielded from the solar light, and then you can have very sensitive camera which is measuring the locations of each one of the stars in our galaxy.
So that's interesting. I didn't know all this.
Yeah.
How big are the Lagrange point areas? Are they really small, or only, you have to be real specific to sit in them, or are they, several miles wide or high, or, in volume?
These points are very different in nature. So basically, this L5 point, and then a corresponding point called L4, which is 150 million kilometers ahead of the Earth on the Earth orbit. They are kind of plateaus, so they are big areas where you can stay. The L1 point and the L2 point, they are kind of quasi-stable points. So it's a little bit like, it's very easy to understand. On one side, you have the gravitational pull of the sun. On the other side of this point, you have the gravitational pull of the Earth. So it's like standing on one leg on a mountaintop. So it's a point where if you slip, you will either fall towards the sun or you will fall towards the Earth. And that's why the spacecraft are not in these points themselves. They are actually orbiting around these points, which is a more stable way to stay in the vicinity of these points. And these orbits around these points are actually very big. For example, in the L2 point, the radius of the orbit of the Gaia mission is about 1 million kilometers. So it's not exactly in this point. It's about it's on an orbit which is always 1 million kilometers away from this point, but it's still a stable way to be there without spending too much fuel on keeping the position of the spacecraft there.
But anyway, so are these points acting as, can you picture it as like a gravity well, or almost like a pseudo body in space that you can orbit around?
Well, it's basically a point of equilibrium. So basically, you have to take the orbital motion into account, but then the gravitational pull of the two main bodies around these points is balancing out. So you can kind of stay there, but as I said, the L1 and L2 point are quasi-stable in the sense that it's really a very narrow region where the pull is equally balancing out. And if you go a little bit away from that, you start to fall. So that's why the satellites are orbiting around these points, which is a sort of a trick to keep the satellite stable there. But the L5 and L4 are more like plateaus. So it's a bigger area. It's actually, I think it's I don't know the exact size even, but it's thousands of kilometers where you can stay somewhere in the vicinity. And doesn't really matter where you are, and then you can stay there.
Space is amazingly weird and fascinating. All the things that happen.
Space is actually, I mean, it's even more amazing that it's not that long ago that we didn't know how to put spacecraft into these points because these calculations of orbital mechanics, it requires a lot of number crunching power. So the utilization of the L1 point and the L2 point only started a couple of decades ago. So before that, we didn't really know how to put spacecraft there. But now our understanding of the orbital mechanics and especially our power to do the number crunching to find the orbits of how to fly to these points has increased so much that now we can start to utilize them.
Well, very cool. Are there any resources for people to find out more about, the mission to L5 and maybe to get a visual map of what, L1 through L5 look like? A picture that shows the sun and the Earth and these points? Yeah,
if you want to understand more about the Lagrange points, then I think there is an excellent Wikipedia page about these points. So I would just advise to go there. Then learning more about the Lagrange mission, we have very nice websites within the ESA website, and one way to find these articles about the Lagrange mission is actually Google for the keywords are where no mission has gone before. If you Google that, you will find a direct link into our website, which will tell you everything you want to know about the Lagrange mission.
Well, that's great. Well, Jussi, thank you for coming and explaining all this, and it's been really interesting. I appreciate you coming on the podcast.
Yeah, thank you very much. It's my pleasure, and I'm available if somebody wants to ask more questions. I will be very happy to provide more information.
Well, how could they contact ESA or you? What's a good resource for them?
Well, you can just Google Jussi Luntama, or you can just go to the ESA website and look for the information about the ESA Space Situational Awareness program, and my contact information is there.
That's great, Jussi. Very good.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.